Back in 1964, physicist John Stuart Bell shook the foundations of quantum mechanics with his revolutionary idea. To understand Bell's theorem, we first need to grasp a couple of key concepts: locality and hidden variables. Locality is the principle that particles can only be influenced by their immediate surroundings. Think of it like a rule that says nothing can travel faster than the speed of light. Hidden variables, on the other hand, are hypothetical properties that we can't directly observe in quantum particles but might still influence their behavior. Now, Bell asked a crucial question: can quantum mechanics, with its bizarre predictions, be explained by a local hidden variable theory? He found that if such a theory were true, then certain mathematical constraints, known as Bell inequalities, would always hold. But here's the kicker: quantum mechanics predicts correlations that violate these Bell inequalities. This means that if quantum mechanics is correct, local hidden variable theories simply can't explain the behavior of particles. Bell's theorem was put to the test for the first time in 1972 by John Clauser and Stuart Friedman. They performed an experiment that showed quantum particles do indeed violate Bell inequalities. This was huge. It suggested that the world of quantum particles is fundamentally different from our everyday experiences. Over the years, more sophisticated experiments, known as Bell tests, have been conducted to close any loopholes that might have affected earlier results. And guess what? These Bell tests consistently found that quantum mechanics holds true, and local hidden variable theories don't cut it. Are particles really connected in some mysterious way? Does information somehow travel faster than light? Talking about free will theorem, do we actually have free will? The theorem asserts that if experimenters have a certain kind of freedom in choosing their experimental settings, then particles also have a certain kind of freedom in choosing their states. In other words, the choices made by particles in quantum experiments are not merely the result of predetermined hidden variables. They exhibit a form of intrinsic freedom. This concept challenges our classical intuitions about determinism and causality. If the theorem holds true, it implies that the universe is not a clockwork mechanism where everything is predetermined. Instead, both human experimenters and quantum particles share a kind of free will, suggesting a more interconnected and dynamic reality. Are our choices truly free? Or are they influenced by factors beyond our control? And if particles themselves exhibit a form of free will, what does that mean for our understanding of consciousness and agency? The Bell test experiments are designed to empirically verify, or potentially disprove, the predictions made by Bell's theorem. They aim to determine whether the correlations observed in quantum systems can be explained by local hidden variables, or if they indeed exhibit non-local behavior as suggested by quantum mechanics. One of the earliest and most famous Bell test experiments was conducted by physicist Alain Aspect in the 1980s. Aspect's experiments involved measuring the polarization of entangled photons. By varying the angles of polarization filters and measuring the correlations between the photons, Aspect provided strong evidence against local hidden variable theories and supported the non-local nature of quantum entanglement. Since Aspect's groundbreaking work, numerous Bell test experiments have been conducted with increasing sophistication. One notable advancement is the use of entangled particles in different locations, sometimes separated by vast distances. These experiments aim to close the so-called locality loophole, ensuring that the measurement choices are space-like separated, meaning no information can travel between them faster than the speed of light. Another important development is addressing the detection loophole. This loophole arises when not all entangled particles are detected, potentially skewing the results. Modern experiments use highly efficient detectors and advanced technologies like superconducting qubits and entangled ions to mitigate this issue. In 2015, a landmark experiment known as the loophole-free Bell test was conducted. Researchers used entangled electrons in diamonds and achieved a near-perfect validation of quantum mechanics by closing both the locality and detection loopholes. This experiment provided compelling evidence that the universe does not adhere to local hidden variable theories, and that quantum entanglement is a real and fundamental phenomenon. While the basic premise of Bell's theorem remains the same, various adaptations and extensions have been proposed over the decades. These variations aim to tackle different aspects of quantum mechanics and local hidden variables, offering fresh perspectives and new experimental challenges. One significant variation is the CHSH inequality, named after physicists John Clauser, Michael Horn, Abner Shimoni, and Richard Holt. This version of Bell's inequality provides a more robust framework for experimental tests, allowing scientists to rule out certain types of local hidden variable theories with greater precision. The CHSH inequality has been pivotal in experiments that further validate the non-local nature of quantum mechanics. Another intriguing extension is the Leggett-Garg inequality, which applies Bell's concepts to macroscopic systems. While Bell's original theorem focused on microscopic particles, the Leggett-Garg inequality aims to test the quantum behavior of larger, more complex systems. This has opened up new avenues of research, pushing the boundaries of what we understand about the quantum classical divide. Then there's the concept of superdeterminism, a controversial interpretation that suggests the settings of measurement devices and the properties of particles are somehow predetermined in a way that conspires to produce the observed violations of Bell inequalities. While this idea challenges conventional physics, it's an example of how Bell's theorem continues to inspire bold and imaginative thinking. Experimentally, variations of Bell's theorem have been tested in increasingly sophisticated ways. Quantum experiments have evolved to include advanced technologies like entangled photons, superconducting qubits, and even satellites. These cutting-edge experiments not only test Bell inequalities with unprecedented accuracy, but also close potential loopholes that skeptics might argue could explain earlier results. For instance, the famous loophole-free Bell test conducted in 2015 used entangled electrons in diamonds to achieve a near-perfect validation of quantum mechanics. This experiment addressed both the locality loophole and the detection loophole, providing compelling evidence against local hidden variable theories. The implications of these variations and their experimental confirmations are profound. They reinforce the idea that quantum entanglement is a fundamental aspect of our universe, challenging our classical intuitions and opening up new possibilities for quantum technologies. From quantum computing to secure communication, the principles derived from Bell's theorem are paving the way for groundbreaking advancements. In summary, the variations and interpretations of Bell's theorem enrich our understanding of quantum mechanics and continue to push the limits of scientific inquiry. They remind us that the quest to understand the universe is an ever-evolving journey filled with unexpected twists and turns.